Okay, hello everyone in a new video. So we have reached part 7 of chapter 2, which is the chapter of electric voltage for grade 10 students. So now in exercise number 18, 7 electric loads are connected to a 24 volts battery as shown in the adjacent figure. Then they mention this figure, now we can use it. So as we have mentioned previously, the trick in solving such type of exercises is to label the voltage on the electric circuit itself in addition to their names. Since we can distinguish always between UPN and UNP, for example. So in this case, the voltage of the battery is 24, so we are measuring for sure from positive to negative. So UPN is equal to 24 volts. Now, given that UPA is equal to 8 volts, and UND is equal to minus 4 volts, UAC is equal to 6 volts, and UBC is equal to 2 volts. So now in number 1, they are telling me to calculate the electric potential differences. So let's start by UDN. Then we are interested in determining UDN. So notice that we have UND. So in this case, no need to apply the law of addition of voltages since they are related by a minus sign. So it's equal to minus UND. Then minus multiplied by minus 4. This is equal to plus 4 volts. So UDN is equal to 4 volts. Then we will not label this voltage because already UND is being labeled. Now in case of UAD, so it can be done using the law of addition of voltages, then apply law of addition of voltages. So always on the left we write the voltage that you are interested in calculating, which is UAD. Then on the other side of this equation, we'll go from points A to D across different electric components such that we know their voltages. Then from A we can go to P, from P to N, and from N back to D. So in this case, if UPA is given by 8, then UAP is minus 8, and UPN is given by 24, and UND is given by minus 4. So plugging this on the calculator, this is minus 12 plus 24, so it's given by 12. Everything previously is expressed in the SI, so the value of AD will be in the SI, which is volts. Then UAD is equal to 12 volts. And let's label this voltage on the electric circuit itself. So UAD is equal to 12 volts. Then we are done with this and this. Now as for the voltage UDC, then let's apply the law of addition of voltages. Then always on the left we write the voltage that you are interested in calculating, which is UDC. Now here we have several ways to go from the point D to C. We can go from D to N, and to P, P to A back to C. Independent of the path followed, we will choose the least or the shortest path, which is from D to A to C. So UDA plus UAC. In this case, previously we have calculated UAD, which is 12, so UDA in this case is given by minus 12, plus UAC, the value of UAC is equal to 6 volts. So this will be given by minus 6. Since this is expressed in volts and this is in volts, so the value of UDC will be expressed in volts. Then UDC is equal to minus 6 volts. So notice here just a side remark, UDC is negative, which means that UCD is positive, which means that the potential at the point C is greater than the potential at the point D, which verifies that the electric current, in this case if we are being asked about the direction of electric current, then it will be from point C to D because C is higher potential compared to D. So we are done with UDC. Now as for the voltage UBA, then let's say apply law of addition of voltages. So in this case, we write on the left the voltage that we are interested in calculating, which is UBA. So from B we can go to C, and from C back to A. The value of UBC is given by 2. If UAC is equal to 6, then UCA is minus 6, then this is given by minus 4 volts. So UBA is given minus 4 volts. And in this case, you can check that the electric current in this case is being traversed from the point A to the point B, because the point A is considered to be a higher potential. Now in part 2, they are telling me the terminal C is taken as electric potential reference. So as indicated here, we are asked to calculate the electric potentials VC, VB, and VA, the electric potentials at the points C, B, and A respectively. So let's start by the electric potential at C. So since C is taken as an electric potential reference, which means that VC is equal to 0. And now let's move to the other point, which is the point B. So notice that in order to calculate the electric potential at the point B, we need to know a voltage that relates this point to another point such that we know the electric potential at the other point. In this case, we can consider UBC, which is equal to 2 volts. Notice that we are interested in determining VB. VB explicitly appears in this equation because UBC can be written as VB minus VC, which is equal to 2. So what's the type of this equation? This is a linear equation, and one unknown, the unknown is VB. Because VC is given by 0, so VB minus 0 is equal to 2. Then in this case, VB is equal to 2 volts. Then we are done with the point B. Now we are interested in determining the potential at the point A. Then in order to determine the electric potential at the point A, we need to know the voltage that relates this point to another point such that we know the electric potential at that point. So notice that we know the electric potential at the point B, we know the electric potential at the point C, but we don't know for the other points. Therefore, we are free to choose either between B or C. Let's choose for C. So we know that UAC is equal to 6 volts. So we are interested in determining VA, which appears here explicitly in this equation. So what's the type of this equation? Linear equation and one unknown. VA minus 0 is equal to 6. Then in this case, the electric potential at the point A is given by 6 volts. Now in number 3, they are telling me an oscilloscope is connected across the terminals of the battery. So in this case, the oscilloscope will either measure UPN or UNP, and this is determined by the connections of the oscilloscope. We observe on the screen a luminous line which is displaced upward. Displaced upward, which means that it's measuring a positive voltage, and the vertical sensitivity is given by 8 volts per division. So they are telling me show on the figure the connection of the oscilloscope, and this must be done by referring to the voltage measured by the oscilloscope to the sine of the voltage measured by the oscilloscope. So let's say since the luminous line is displaced upward, then the oscilloscope measures positive value, and knowing that UPN is positive, then the oscilloscope is measuring UPN. Since the oscilloscope measures UPN, then the phase terminal is connected to P, and the mass terminal is connected to M. So this is the phase terminal and this is the mass terminal. Now in part B they are telling me calculate the number of divisions, which is the value of y, and this can be done using the formula U is equal to SV multiplied by y. Notice that here we are measuring UPN and we are interested in determining y. Flipping this equation, then SV multiplied by y is equal to UPN. Then dragging SV to the right, it will be divided, then y is equal to UPN divided by SV. The value of UPN is given by 24 and the value of SV is given by 8, so this is equal to 3. Since the vertical sensitivity is volts per division and UPN is in volts, then the value of y will be divisions. Notice that y can be expressed either in divisions or centimeters, and this depends on the unit of SV. Notice that here the value of y is positive, which verifies the fact that the oscilloscope is measuring UPN and not UNP, because the luminous line is displaced upward. So y is equal to 3 divisions. Now in part 4, an analog voltmeter of non-centered needle of DLD is equal to 100 divisions and having the following scales is used to measure the potential difference between P and A. So we are measuring the voltage UPA, which is equal to 8 volts. So show the connection of the voltmeter. The voltmeter is distinguished by the COM terminal. So let's say since the voltmeter measures UPA, then the COM terminal is connected to A, and the other terminal is connected to B. And you know that the voltmeter must be always connected in parallel, so this is the voltmeter. And the COM terminal is connected to A because it's measuring UPA. Wait, an analog voltmeter of, okay. So, okay, here they didn't mention that whether we are measuring UPA or UAP. So I have chosen to be UPA. So here let me say as a given, it's measuring UPA. So suppose that this is a part of the given, okay? So suppose that this is a missing statement. Okay, Now in part B, they are telling me from the above scale, specify the most adequate one. Adequate means convenient, and this always can be done by referring to the definition of the convenient scale. So let me write it here. The most convenient scale is the one having a value slightly greater than to be measured. So in this case, if you are measuring UPA which is equal to 8 volts, then the most adequate one is given by 10 volts. 10 and 15 both, so 1 and 5 are eliminated because they are less than 8. Then we are left with 10 and 15. 10 is the one which is slightly greater than 8, so in this case the most convenient scale is given by 10 volts. So now we have specified the scale which is given by 10 volts. They are telling me in part 6, calculate the deviation of the needle, and this can be done using the formula U is equal to S multiplied by D divided by capital D, in which U represents the voltage, capital D the dial, S the scale, and D the deviation of the needle. Flipping this equation down, knowing that we are interested in determining D, then S multiplied D divided by capital D is equal to U. Notice that here we are measuring UPA. So moving capital D to the other side, it will be multiplied. Moving S to the other side, it will be divided. Then D is equal to UPA multiplied by D divided by S. So this is equal to 8 multiplied by 100 divided by 10. So this is 80. Since everything is expressed in the SI, so this is volt, this is volt, this is division. This will cancel out with this, so D is expressed in divisions. So in this case, D is equal to 80 divisions. Now moving to exercise number 19, they are telling me in the given circuit diagram the loads are identical. Okay, so this is important. And UPN is equal to 12 volts. Now in number 1, they are telling me the switches K1 and K2 are open. So before we start calculating or answering the questions, let's analyze the circuit. So notice that because K1 is a open switch, so it can be connected, because notice that this part is a connected wire connected to one terminal, so it can be neglected or ignored, and this wire is only connected to one terminal, which can be ignored. As for the switch K2, so this is a connecting wire connected to one terminal, which can be ignored, and the same goes for this. So let's ignore them. Now we are interested in determining UAB, UCD, and UBC. So in order to determine UAB, knowing that the loads are identical, it's sufficient to determine UAD and divide the voltage by 2. So first let's determine UAD, and this can be done by using the law of addition of voltages. So apply law of addition of voltages. So in this case, we are interested in determining UAD. So going from A to P plus P to N and N back to D, knowing that UAP is equal to 0, and the reason is given by a connecting wire. UPN is equal to 12 volts, plus U and D. Across N and D we have a connecting wire, so this is 0. So this is equal to 12 volts. So knowing that now UAD is equal to 12 volts, so we are looking at the upper part, because we are interested in determining UAB. If UAD is equal to 12 volts and these two loads are identical, so let's say since Let's suppose that this is D1, D2, D3, and D4. Since D1 and D2 are identical, then they have the same voltage, which means that, so how do we translate this statement into mathematical formulation? What's the voltage across the loads D1 and D2? They are given by UAB, which is equal to the voltage to the another voltage, which is UBD. Now the point B will be eliminated and we are left with UAD divided by the number of loads, which is 2. Notice that here actually the number of loads between A and D, they are 4, but what's important to consider the loads that are in series. So here if you are looking at the upper part, you have 2 loads in series. If you are looking at the lower part, we have 2 in series. Okay, so we don't consider 4 loads. Okay, and simply here the reason, because in order for this point to be eliminated, okay, so if we need to include AC and CD, this will not work out. Okay, so this is given by 12 divided by 2, which is equal to 6. Since everything is expressed in the SI, so this is in the SI, which is volts, which means that UAB is equal to 6 volts. So here we have that UAB is equal to 6 volts and UBD is equal to 6 volts. Okay, so we are done with UAB. We are also interested in determining UCD. So UCD can be done in the same way. Let's say now we have already determined the voltage UAD, which is equal to 12 volts. No need to repeat this step. And let's say since D3 and D4 are identical, then they have the same voltage. Which means, okay, how can we how can we make use of this statement in the mathematical form? So what's the voltage across D3 and D4 that they are equal? The voltage across D3 is given by UAC, and that of D4, which is given by UCD. And notice now in this case these 2 points eliminate each other and we are left with UAD divided by the number of components, which is 2 and not 4. So here, because we have 1, 2, so 12 divided by 2, which is equal to 6 volts, then in this case UCD is equal to 6 volts. Now after we have determined the voltage UCD, we are asked to determine the voltage UBC across the points B and C. Although no electric component exists between these two terminals, but for sure we can calculate this voltage. So let's say apply law of addition of voltages. So we are interested in determining UBC, then from B we can go to D, and D back to C, knowing that UBD already calculated, which is 6, and UDC, if UCD is equal to 6, then UDC is given by minus 6, so this is equal to 0 volts. So UBC is equal to 0, and let's interpret this result. So here notice no need to write the unit because anything multiplied by 0 is 0. So let me interpret the following result. We know that whenever we have a connecting wire, then the voltage is given by 0, but the converse is not always true. Okay, so now UBC is equal to 0. This doesn't mean that BC is a wire. This is not true. Why? Because we know that if this electric component obeys Ohm's law, so U can be written as R multiplied by I. So in this case we have that either R is equal to 0 or I is equal to 0, and this is important here that it's given by OR. So this is true or this is true. This is the case of a connecting wire. Okay, so for this reason this is not true, and we are left with that the electric current between the point B and C is 0. Okay, so notice that this is one of the explanation why UBC is given by 0, but this is also not necessarily true, because we know that in other cases where we don't have anything connecting the points B and C, we can also measure a voltage. Okay, so later on in the chapter of generator and receivers we will talk about this in more detail. Okay, so now in number 2 we have reached number 2. So now in number 2, switches K1 and K2 are closed. So let's close the switches, and the moment we close the switches everything will change. So let's close the switches. So now because we have closed the switches, let's do the following analysis. Notice now, so if this is the electric component D1 and this is D2, this is D3 and this is D4. So notice now the electric component D4 is short-circuited because simply it's in parallel with the connecting wire. The voltage across a connecting wire is 0, and according to law of uniqueness of voltages they have the same voltage, which is 0. So this electric component is considered now as a connecting wire because it's short-circuited. So its voltage is given by 0. And notice that now the electric component D2 is in parallel with the connecting wire. So in this case, so first let me say that UCD is equal to 0, and the reason is given by short-circuited. Moreover, also UBD will be 0 because notice that between the points B and C we have a connecting wire, so the potential at the point B is equal to the potential at the point C, and the point D is a common potential. So UBD is equal to UCD. So D2, the voltage across D2, which is UBD, is also 0 because they are in parallel with the connecting wire. So first let's determine the voltage UAB. Now UAB must be determined using the law of addition of voltages, because notice that we cannot say that UAD, for sure now UAD is equal to 12 volts, because we can calculate this using the law of addition of voltages from moving A to P, P to N, and to D. Okay, but here we need to be very careful. We cannot say that now A and B, D1 and D2 are identical, then they have the same voltage, because notice now the electric component D2 is not functioning anymore because it's simply in parallel with the connecting wire. Okay, so let's say apply law of addition of voltages. So in this case we are interested in determining UAB going from A to P plus P to N plus N to D and D back to B. So UAP is equal to 0 justified previously. This is 12, UND is 0, and now UDB is 0, and the reason is given by short-circuited. So in this case this is equal to 12 volts, then UAB is equal to 12 volts. Now they are asking me about the voltage UBD, but we have already used this voltage, so we can say that UBD is equal to 0, UDB or UBD, they are the same, and the reason is given by short-circuited. So we are done with UAB and UBD. As for UAC, We can say that it's in parallel with UAB, so it's given by 12, or we can use it, determine it using the law of addition of voltages. So let's say apply law of addition of voltages. Then from A we will go to P, or let's choose another easiest path, or the shortest path from A to B and B to C. So UAB is equal to 12 previously calculated, UBC is equal to 0, and the reason is given by that UBC is equal to 0, close the switch. So this is equal to 12 volts, then UAC is equal to 12 volts. And we are done with this. We are interested now in determining UAD. UAD can be determined using the law of addition of voltages. So here let me say that UCD equal to 0, UBD is equal to 0, UAB is equal to 12 volts, and UAC is equal to 12 volts. So now apply law of addition of voltages. Then from A we will go to B, and from B we will go to D. So this is 12. Now UBD is equal to 0 because D2 is parallel to a connecting wire. Why parallel to a connecting wire? Because notice that the point B is common for this wire, and the point D is common for this wire. So they have two terminals in common, the electric component D2 and the wire. So this is equal to 12 volts. So UAD is equal to 12 volts. And now as for UBC, simply UBC is equal to 0. So the voltage, or we can directly say close the switch, because the voltage across a closed switch is 0. Now as for exercise number 20, they are telling me in the circuit of the adjacent figure UAB is equal to 30 volts. In number 1, they are telling me give the value of UBC if. So notice that UBC represents the voltage across the switch S2. S2 is in series with the battery. So if it is open, then it will have the same voltage of the battery up to a plus or minus sign. If it's closed, it will be 0, independent if S1 is open or closed. So here in this case, we can neglect these statements. So they are just present to confuse us. Now if S2 is closed, then simply UBC is equal to 0, and the reason is given by close the switch, or the voltage across a closed switch is 0 because it acts as a connecting wire. If S2 is closed, then UBC is equal to 0, close the switch. Now in 1.3 S2 is open, so it has the same voltage of the battery up to a minus sign, and it depends that whether we are measuring UBC or UCB. So since we are measuring UBC and B represents the negative terminal, so we're measuring from negative to positive, then UBC is equal to minus 12 volts. So let's say an open switch in series with the battery has the same voltage of the battery. In this case, UBC is equal to minus 12 volts, sorry, minus 30 volts. Now in number 2, they are telling me S1 and S2 are now closed, so we deal with them as connecting wires. Now they are telling me UCD is equal to minus 10 volts. UAG is equal to 8 volts. And UFE is equal to UED, so this is important. So let's say that UFE is equal to UED. So this can be the case of identical electric components in series. Now in 2.1 they are telling me calculate UFG, and this can be done. Okay, so this cannot be done using the law of addition of voltages because we have several unknowns. Notice that the electric across F and G we have two components. Either we can consider this component or the wire. So we can simply say that UFG is equal to 0. The reason is given by connecting wire or short circuited. They are the same. So we are done with UFG. Now UFD. Okay, so we are interested in determining UFD, and this can be done using the law of addition of voltages. So we are interested in determining UFD, putting it on the left and going from F to G, G to A to B, B to C, and C back to D. Now UFG is equal to 0 justified previously. UGA, if UAG is 8, then UGA is minus 8. UAB is 30. UBC is 0, and the reason is given by closed switch. So let's see it justified between the brackets that UBC is equal to 0. The reason is given by closed switch. And as for UCD is equal to minus 10. So this is minus 18 plus 30, so this is given by 12. If everything is expressed in SI, which is volt, then UFD is equal to 12 volts. So if the applied voltage across the terminals of F and D is given by 12, and notice that in this case we can eliminate this point, and this is given by UFD divided by 2, so this is equal to 6 volts. So each electric component share an applied voltage of 6 volts. So we are done with UFD. Now they are telling me to determine UMD. Now, in order to determine UMD, we can go from M to F, F to G, G to A to B, B to C, C back to D, but we can choose another path which is given by from M to F, F to E to D. So, but actually we don't know F, E and ED. So, okay, let's consider the following. Apply law of addition of voltages. Knowing that we are interested in determining UMD, so from M we can go to F. Now in this case we can determine UFE and UED because they are equal in value, but notice that because we know UFD we can directly go from F to D. And okay, so this is a valid equation because we have started with M, ended with D, and we have inserted each letter twice. So UMF is equal to 0, and the reason is given by closed switch. And what about UFD is given by 12, so this is 12 volts. So UMD is equal to 12 volts. So we are done with UMD. Now as for UDE, now since we have the following equality that UFE is equal to UED, no need here to say since they are identical then they have the same voltage, because we say that statement in order to reach this point, but we are already in this point, so let's eliminate this point, and this is given by UFD divided by 2. So it's given by 12 divided by 2, which is equal to 6 volts. So in this case, UED is equal to 6 volts, which means that UDE is equal to minus UED, which is equal to minus 6 volts. So UDE is equal to 6 volts. And notice that all the required voltages, I'm placing them in a box, and there are some intermediate values. Okay, so UDE, so this is equal to 6 volts. Now what about UCG? So we can determine the voltage UCG from going to C to G across the points B, A, and G. So apply law of addition of voltages. Then we are interested in determining UCG going from C to B plus B to A and A back to G. UCB is equal to 0, justified previously. If UAB is 30, then UBA minus 30, and UAG is given by 8, so this is minus 22 volts. Then UCG is equal to minus 22 volts. And notice that across C and G we don't have any electric component. Okay, now in 2.2 they are telling me if point D is connected to the mass, so the point D is considered the mass terminal. We are interested in determining the electric potentials of the points C and F. So let's say that VD is equal to 0, electric potential reference. Now we are interested in determining the electric potential at the point C. So in order to determine the electric potential at the point C, we need to consider a voltage that relates this point to another point, such that we know the electric voltage on the other point, and this is given by UCD is equal to minus 10 volts. And here we can notice the importance of labeling the voltage on the electric circuit itself. VC appears explicitly in this equation because VC minus VD is equal to minus 10. This is a linear equation, and one unknown, the unknown is VC. So the value of VD is 0. So in this case VC is equal to minus 10 volts because everything previously is expressed in volts. And now as for the electric potential, at which point? At F. So in order to determine the electric potential at the point F, we need to know a voltage that relates this point to another point, such that we know the electric potential at that point, and this is done by UFD. I didn't consider the point E because we don't know the electric potential at the point E. However, we can determine the electric potential at the point E, then determine that of F, but we are chasing the easiest or the shortest path. For example, we can say, because we know UMD, we can determine the electric potential at the point M, and VF is equal to VM because across F and M we have a wire. So now the easiest one is to say that UFD is equal to 12 volts, knowing that VF explicitly appears here. So this is a linear equation. Minus 0 is equal to 12, so in this case VF is equal to 12 volts. And by this we have finished solving this exercise. So that's it for me in this video, guys, and this is the last part of this chapter.